Hi guys, in this video we are going to see how the half wave rectifier circuit works. Okay. If you like this video, I request you please click the like button and subscribe button to get more updates in advance later videos. Okay. Yeah, thanks. Let's go into the topic. See, what is in the rectifier? Rectifier is the circuit which converts AC input into DC output. Input will be AC and output will be DC. That converter circuit is called rectifier circuit. Okay, in the same way, if the input is DC and output is AC, that's called inverter, opposite to the rectifier circuit, right? The function is exactly opposite to the rectifier circuit. Okay. So now come to the half wave circuit. Okay, let's first get into the various types of rectifier. Now we come to know what is in the rectifier, right? What are various types of rectifier? Based on the controllability, we can say uncontrolled rectifiers and controlled rectifiers. The uncontrolled rectifier means the output voltage cannot be controlled. The output voltage, output DC voltage. So input is AC, output is DC, right? The output DC voltage cannot be varied. That's called uncontrolled rectifiers. The name says that uncontrolled. You cannot control the output voltage. So in uncontrolled rectifiers, we are using the diodes as the components. Okay. In the same way, what can be controlled rectifiers means the output voltage can be controlled. There we are using, instead of diode, there we are using SCRs, switching devices, BJT or MOSFET, right? By varying that base drive current or gate voltages, we can vary the output voltage. We will see in later videos the controlled rectifiers. Okay, based on the period of communication, how long it can be, the rectifier can be classified as the half wave rectifier and full wave rectifier. So half wave rectifier means just rectifying the control during one half of the AC cycle only. That diodes are there, right? We are using that. Right? It connects during one half of the AC cycle only to convert. The other half of the waveform it will suppress it, output it will not be applied. In full wave rectifier, both positive half cycle, negative half cycle can convert it and it will come into the output cycle. Okay. Now I like to add one important point. The half wave rectifier circuit in real life, in practical, in commercial purpose, we never use this one. This is just for theory purpose only, just for understanding to proceed further what how bridge rectifier works or how full wave rectifier works or how SCR based rectifiers are working. Okay, yeah, now get into the topic. And one more thing here, semi-controlled and fully controlled. What does that mean? Yeah, I think it's instead of going into that topic, we'll just go into the after rectifier, a very basic type of rectifiers. Okay. This is the after rectifier circuit, right? So the input AC voltage will appear across the primary side of the transformer. The other side of the transformer, we are connecting on diode and load resistance. So the DC output will be the Dout is the output, and it will appear across the load resistance. Okay, so this is the input waveform, AC waveform, a sinusoidal AC waveform here, right? So during positive off cycle, the plus, the A point A will be the plus and point B will be minus. That means point A will be high potential compared with respect to the point B, right? Whereas in negative off cycle, it will change. B will be more positive than B, right? So it will cyclically change. If during positive off cycle, A is in plus, right, and B is in minus. That will keep in mind. Next, come into the diode. Diode is see, this is the diode symbol, and here it's an anode, and this is the cathode. So when it is forward waveform, means when anode is high potential compared to the cathode terminal, or when anode is connected to the positive side of the supply and negative side to the cathode, then it is in forward bias, right? You agree with me, right? So, and the diode is known as Diode is a solid state switch. That means it will allow the current in only one direction, from anode to cathode, in the forward biased condition. That means when anode is more positive than the cathode. Okay. And when the cathode is more high potential compared to the anode, then it will not conduct. Right? And this you got it, right? So this is one thing. So here come into the point. Um, the input voltage, AC sinusoidal input voltage, that across the A and B, secondary of the transformer, right? During positive half cycle, A is more positive than B, right? So diode is in forward biased condition. That means diode is in act as a closed switch. So it allows the current to flow through the load resistance. So the output voltage will appear across the load resistance, correct? Current flows through this one, and the cycle will close in this one. And when during negative half cycle, B is more positive than A, correct? How in that case, how will be? The cathode is more positive than anode. That means then the diode will be in open condition, correct? And diode is in reverse biased condition, and that means it is in the switch is in open condition. Right? So this is the output current and the voltage waveforms. You can observe here, right? Only positive obstacles are reflecting here. Negative obstacles are suppressed, right? So we are considering as ideal diode. That means there is no voltage drop across the in the diode. Right? There is also some forward resistance drop, some percentage RF forward resistance drop, something will be there in diode. That is very minor compared to the negligible compared to the load resistance. Right? So the same amount of input voltage will appear across the output side, and the frequency will be same actually. See input, this is the input waveform, correct? So for every cycle, every one cycle, out also only one cycle will appear. The negative offset is suppressed, is 0, right? Whereas in case of full wave rectifier circuit, the negative offset will also get converted, and here also the same sinusoidal waveform. So in full wave rectifiers, the output frequency will be 2 times that of the input frequency. Okay. So in a critical manner, I refresh once in the operation of the Half Wave Rectifier circuit, right? So the input AC sinusoidal waveform then applied across the half wave circuit. During positive half cycle, the diode is in forward biased and it will conduct the current through the load resistance. So the output voltage will appear here. And during negative half cycles, the diode is in reverse biased, so there is no current flow across the load resistance, and there is no, as you mentioned, 5 to 2 pi, this is 0. Okay, this is the operation. This is a basic operation of the half wave rectifier. If you understand clearly this one, the half wave rectifier circuit and that output current waveforms and the Irms current, average current, deriving those values, then that is the fundamental form to go further into the bridge rectifier related circuits and their related calculations and fully controlled SCR based rectifiers calculations that will be used. Okay, so this is what so here you find this. See, now we are going to find the average value of the output DC. Actually, output DC we have to say the pulsated DC. We have to say this waveform is called after rectified waveform or pulsated DC waveform. Right? Okay, so this is the instantaneous values from there. So average value. What is the if you say DC output we are saying is a DC. So what is the DC value? IDC value, whether here or it goes here or we have to see it. So to find it out that one, average value will be always. See for average value will be area under this curve. See this is the value right here, area under this curve, and what is the time period? The period is 0 to 2 pi. Okay, period is 2 pi. The value area under the curve means we have to find the area here. So it follows the sinusoidal waveform, right? Vm sin omega t, or sin theta. Vm sin theta. Maximum value is Vm if you say it. Vm sin theta it follows. Yeah, here it mentioned that. See, base will be the 1 by 2 pi. The 2 pi is the base period. Okay. So we have to find the area under the curve. and during the 0 to pi it follows the sine form, and pi to pi 2 pi this is 0, right? So we are ignoring the value, only 0 to pi I d theta. I value is Vm, I is d by r, right? V value is Vm sin theta into d theta. So Vm and RL are constants. So we are taking outside and integration of 0 to pi sin theta d theta. So integration of sin theta is minus cos theta. Substituting the values of pi and 0 in the theta values, we are getting 2. And simplifying this value, we can get as IN by pi is the average current for the half wave rectified waveform. Okay? This is the average current. To get the RMS value, there is base. The in the base may mean that the area under the square beta. Right? RMS value is a DC equivalent of the AC wave. Right? So area under the square value is the base. And these are the form factor and the ripple factor. We have to every rectifier, their performance, their efficiency are determined by the form factor, ripple factor, and peak factor. So in these values, we can compare the whatever positives and negatives of each and every rectifier software. Okay. So I think it's good to derive once again in almost each and every step by step of these calculations. And if you like this video, please click the like button and click the subscribe button, guys. And we'll see on a part 2 of this